All right, well, hey, welcome to week 2. We are 1/12 of the way done with the quarter. It flies by, but anyway, so welcome to week 2. Before we get going into new material or really continuing with what we were talking about last time, talking about limits, I just wanted to open it up to any homework questions. But I do know that someone sent me an email about one of the questions from one of the earlier sections, the sections on composition. So I want to go ahead and kind of walk through that one real quick, or at least one that was similar. And then I'll turn it over to you guys. So let me go ahead and share my screen here. I'm going to turn on the whiteboard. And this was the problem that looked something like f of x. So we were doing composition, but we were doing the same function 3 times. So let me show you how this would play out with an example function. I don't know what function you had in yours. Doesn't really matter. But let me start by drawing the little picture of the machines, right? So the little function machines where we drop in a number, something comes out. So this one, since we've got f of f, there are actually 3 of these. And they're all in sequence. And they're all f, right? So in this case, since it's f of f, each of these guys is an f of x. And when you do composition, you can absolutely compose the same function with itself. It's just copies of the same thing. So we just link them together like normal. So let me start with just a number so we can kind of see what would happen. Like let's say we started by plugging in 1. So we would begin with f of 1, which would say to square 1 and add 1, right? It always says square what you put in and then add 1. So this would equal 2. So that means that 2 is popping out of the first function, which means 2 is now falling into the second function. Well, it turns out that it's f again, but we're going to do exactly the same thing. You're going to take that 2 and square it and add 1, because that's what this rule says to do. So 2 squared is 4, plus 1 is 5. So out pops a 5. Now that 5 immediately drops in to the next function, which happens to be f again. So we're going to do f of 5. Well, the rule said square that number and add 1. So that gets us 26. So what finally pops out is 26. So we started with 1 and we ended up with 26. Excuse me. So basically what we just figured out is that f of 1 is equal to 26. Now, often we don't want to plug in a specific number like this 1. We just want to leave it as an x. So it ends up that we do exactly the same thing. It just makes it so that we've got different inputs, which means we end up with different outputs. So let me change my color here. So now let's do f of x. So now we're putting x in. Well, what's going to come out of the first function is x squared plus 1, because that's the rule. Now this x squared plus 1 is going to get dropped into f. So that means we need to do f of x squared plus 1. But the rule says take what you're plugging in and square it and add 1. So what we're putting in is x squared plus 1. We're going to square it and add 1. That should be a 1, not a 4 looking thing. Sorry about that. Okay. So when we square this, we're going to get x to the fourth plus 2x squared plus 1, which is x to the fourth plus 2x squared plus 2. And that extra piece, 2x squared, comes from foiling. Don't forget, you can't just pass a square through here because of the addition. What's really going on is you got x squared plus 1 times x squared plus 1. And if you FOIL that, that's where all those pieces come from. Well, that then is what we've got right here. That's what came out of the second function. And now we're going to go and drop it in one more time. So we're going to do f of x to the fourth plus 2x squared plus 2. And the rule says, take that thing that we're plugging in, square it, add 1, and then you would just do your algebra on this. Again, you'd have to multiply it out. But that would then be f of f of f of x. So the trick is just keep putting in that rule, whatever that rule is, use that rule, and make sure you just sort of follow it in order. So if it helps to draw the picture, draw the picture. But just realize that you can compose the same function repeatedly. It's totally fine. All right, so questions on that? So Aries, you just said, could you write the final answer? Instead of foiling it all out, can you just leave it as those things squared? Can you? Absolutely. If this was an exam or a quiz, something that I'm grading, I would give you 100%, so 10 out of 10 or whatever. As for what the computer wants, I can't answer that. Sometimes it's a little bit cranky and wants something specific. So I don't know the answer. But if you were to put this in and it says no, most likely then it does want you to expand it out. And it doesn't take that long. But yeah, I'm with you. I'd rather just write it out the quick way than expand it all out as well. All right, other questions on this one? Okay, so what about other questions? Were there other questions on the homework?
Can you go over instantaneous rate of change? Because I think I just didn't round correctly, and then the computer system counted me wrong the first time, but then the second time I went back, and then I got some of the questions correct.
Sure, we can talk about that. In terms of instantaneous rate of change, at least where we are right now, all we're doing is getting approximate values, right? We're going to get our best guess of what instantaneous rate of change is, because we don't know calculus yet. We haven't developed the derivative, which is going to be the tool to find instantaneous rate of change. So if you're ever asked at this point for an instantaneous rate of change, it's going to be just an approximation. It's going to be a guess, as opposed to an average rate of change, which we can definitely calculate, and it is going to be what it's going to be, right? It's the change in y or change in x. It's the slope. So was there a specific problem, Susanna, a specific problem number you wanted to look at, or you just want me to make one up?
I don't know what it was on homework, but I'll just go back to like later today and then come by your office hours if I find a specific one.
Okay, I can just make it up.
Mm-hmm.
It's not a problem.
Thank you.
So let me go ahead and share a whiteboard again. So go ahead and clear this. All right. So let's just go with a function like f of x equals x squared. Okay, so we'll make it simple, but not so simple that finding an instantaneous rate of change is trivial. So let's just go with x squared. And let's find the, or approximate the instantaneous rate of change at, let's say, x equals 1. Okay, so if you were to draw the graph of this thing, we got ourselves x squared. So we're somewhere out here at 1, and we want to find the instantaneous rate of change. So what we talked about last time is that that's the, oh my God, let's try that again. It's the slope of the tangent line Okay, so we're looking for the slope of that thing. Now, if we had a really, really good graphing program and we drew that line just perfectly, we could actually find 2 points on that line, calculate its slope, and go, well, that's our best guess. So Eris just says, is there a better way to get the tangent other than eyeballing it? Not right now.
I keep getting mine wrong online, and I've tried it like 5 times.
Okay. Well, let me give you some ideas on how we can get a better guess instead of just eyeballing it and hoping that we're right or close enough or whatever the computer is going to say to us. All right. So here's what I would do. I would start by going with, well, let's just look at 2 different x values. So we got an x value of 1. And let's just go out a little bit over on the function. So I just put an x there, meaning that's where I want to look. And find the slope of the line that connects these 2 points. So at 1, I know that we're at 1, 1. So here's what I would do. Again, I would make a little chart, and I think we made a chart kind of like this when we were talking about limits. So we'll kind of set this up the same way. We're going to go with an x value. Let's do a f of x value. Then I'm going to put a change in y, a change in x, and a slope. Okay, so at 1.1, my f is going to be 1.21, because that's just 1.1 squared. So my change in y is 0.21, right? Because we were at a 1, now we're at a 1.21, so we've gone up by 0.21. My x is 0.1. So my slope then is delta y divided by delta x, right? Change in y over change in x, which gives me 2.1. So that's an approximate value for the slope. Well, if I want a better guess, I'll bring that second point in closer. So instead of being out here, let me bring it here. Those 2 points still form a line. That line is still a secant line, but it's going to get me a better guess for the instantaneous rate of change. Because this 2.1, this is an average rate of change. It's the average rate of change between 1 and 1.1. But we're going to use these average rates of change to give us a guess for the instantaneous. All right, so we're going to do the same thing. F of 1.01 is 1.0201. When I subtract off the 1, I get 0.0201. My delta x is now 0.01, which then gives me an m, a slope of 2.01. So there's another average rate of change, but it's an average rate of change over a smaller period. So again, imagine that this was some object that's moving. We just found its speed, let's say, over an interval that's 1/10 of a second long. That was this. Now we found its speed over an interval that's only 1/100th of a second. And so if we keep shortening that time period, say, we should be more confident that the actual speed is close to what we're calculating as our average speed. Right? Think about this as somebody who's skiing down the mountain and we got our stopwatch on them. If I average them over like a 10-second period, that's a lot of opportunity for them to speed up or slow down depending upon what's going on. But if now I shorten that to 1 second, it's not going to be as variable. 1/10 of a second, definitely not very variable. 1/100th of a second, I don't think we would notice a difference. And so that's what we're doing here. We're trying to make that time period so small that it just feels like, yeah, it's pretty much what our speed is. So let's try one more here. Let's go to 1.001. I'm going to write it down here because I'm running out of space. I square that. I get 1.002001. So my delta y is 0.002001, which makes my delta x, in this case, 0.001. So if I calculate my slope, I get 2.001. So over a time period of 1/1000th of a second, this is my average rate of change. So if you had to make a guess, what do you think our instantaneous rate of change would be? All right, I just saw Susanna do this for me. And I'm guessing that's not some sort of a math gang sign, but maybe it is. So a lot of you are throwing out 2. And I think, yeah, it seems reasonable. As we make those steps smaller and smaller, right, as we get closer and closer, that slope seems to be getting closer and closer to 2. So in this problem set, when they say what's the instantaneous rate of change, you're making your best guess. If you put in something and you think that it's pretty reasonable, but the calculator is still saying it doesn't agree, shoot me a note, send me a message so I can look at it, because I can go in and I can override that score. I can give you the points. And if it's one of those things where, let's say for this problem, you put in 2.001 and it says no, and you try again and it's actually looking for like 2.00001, to me that's whoever programmed this was being kind of dumb, let's just say. They weren't really thinking about it, and they weren't allowing a tolerance when there absolutely needs to be in this case, because we're just making a best guess. And a guess of 2.001, if the actual answer is 2, is a pretty good guess. I would say 2.01 is also a pretty good guess, right? So if you end up having issues like that where it's a decimal thing, like you give them 3 decimals, but they wanted 5, unless they specifically state it, right? Because there are some that will say, put in your answer to 4 decimal places or something like that. So if it doesn't specifically state how many decimals, and you run into that kind of issue, please send me a message, because I can do 2 things. One, I can change your score, give you the points, but I can also contact people that program this stuff and say, hey, let's give them a little bit more tolerance on this kind of a problem, because this isn't an exact thing. All right, so is that good, Susanna? Yeah. Okay, and then somebody was just jumping in. Sorry, go for it.
On some of them that just gives you a table of data. It was like successive Friday, the millions of receipts for the movie Avatar. Do you just plot that into a scientific calculator and get your own equation and then do this?
I wouldn't necessarily go with an equation. I would just use those data points as my X's and Y's. Because like here, I had to calculate my Y's. If you're given a list of data, those are giving you your Y's. So if I'm kind of understanding you correctly, Vale, is you have something like this where it's maybe year and it's dollar amounts, right? And so maybe we have, say, 2008, 14.2, 2009, 16.1 or something like that. Then my average rate of change is, again, just the slope. So what I can do is just take those numbers as my X's and my Y's, and then do good old change in Y over change in X.
What about the instantaneous for this kind?
Okay. So again, you're making your best guess. Let me do one more thing. Let me put in another number here. Let's say we got 2007. And so they say, find an instantaneous rate of change for 2008, let's say. So like this one would give me an average from 08 to 09. So I guess that would be like 1.9, right? I could also do 2007 to 2008. Which would give me, what, 0.8. And so what I could infer from this is that my instantaneous rate of change is somewhere between 0.8 and 1.9. And so without any other information, without any better information, I would probably just split the difference in these. And I think that would put me at like 1.35. So then Arius says, could you do 2007 to 2009? Sure. That's still also going to be an approximate. Let's see what happens if we do 2007 to 2009. We'd have 16.1 minus 13.4. Let's see. So the difference in that is 2.7 divided by 2, which, oh, hey, look, is exactly that same number. Now, that may not be exactly the same, but it would at least be probably very similar.
Thank you.
So I think what you're looking for here is something that I can't give you, not because I don't want to or whatever, but because it's impossible to give you. It's impossible to get an instantaneous rate of change for 2008. If all we're given is data. So all we're doing is making our best guess. And in my experience, students hate that in math because we're so trained that there is the answer. This is the way of doing it. But when it comes to something like approximations, there is not a way of doing it. And for those of you that are really going to be going into the sciences, I want you to realize that almost all science is approximation. It's very, very rare that you ever get exact values. You're always getting best guesses. And the reason that that happens is that math is not the real world. When we're in here doing math, we may use real world numbers, but math itself has a specific set of rules that always are. There's no getting around them. So there's no variability. And that's why when I say solve this equation, there is an answer. But then when we try to use math to assist us with real life situations, we are presented now with real life variation, right? The real world doesn't give you lines. The real world doesn't even give you quadratics. The real world doesn't even really give you polynomials. We get all kinds of weird stuff out there that mathematically is a lot more complicated. And there's just a lot of variability. And so a lot of it is winging it and going with, well, I don't know exactly what it is, but it's around 1.35. And then we try to refine our data taking, our experimentation, whatever, so that this approximation fits better or we're more confident with it. But in the end, we're still just guessing. We're winging it. Anyway, I'm starting to preach, so I'm gonna stop. Let me stop sharing there. All right, so are there any other homework questions out there? Are we ready to
excuse me.
Yeah, go ahead.
I don't know how to find the inverse trigonometric function of the tangent, like in homework exercise 1.4, the number question 8 and 9.
Okay, I think I remember that kind of problem. So let me just put one up here real quick. Go back to the whiteboard. So Fenrir, let me know if this is what you mean. Something like inverse tangent of cosine of 2/3. Is that similar?
Inverse similar, but I think this is okay, but I'm not sure, like inverse tangent of the tangent.
Okay.
And with a very big number, yeah.
So inverse tangent of 73, something like that.
For like 41 pi over 11, like that.
Oh, okay.
Yes, yeah.
We can do that. Inverse tangent of tangent 41 pi over 11. Okay. So let's just forget about all that stuff. All right. So obviously the inverse tangent undoes tangent. So here this is saying we're taking the tangent of an angle. It's giving us a number. And then inverse tangent is bringing us back to an angle. So the most important thing to remember with these were the restrictions on the angles that we had to put in to allow for the inverse trig functions. So like for sine, inverse sine will only ever give you angles that are between minus pi over 2 and pi over 2. This was a restriction that was put in so that sine is 1-to-1 and has an inverse. Similarly, for inverse cosine, it was between 0 and pi. And then for inverse tangent, it was between minus pi over 2 and pi over 2, but not including the endpoints like with sine, because tangent's not actually defined at either of those endpoints. Okay, so basically what you have to do when you have one of these problems is you look and see, is this angle that we're given, is it in this interval? Because if it is, then the inverse tangent and the tangent would cancel each other out and we would be done. And so, for example, if it had been, let's say, tangent inverse of tangent of pi over 7, pi over 7 is in this interval, so it would just be pi over 7. So best case is when your angle is in this restricted interval, and then you're just done. Now, this specific one that we made is not in this interval. 41/11 pi is somewhere between 3 and 4 pi, which is way too big. So what we need to do is backtrack until we get into this interval. So basically what we need to do is let's figure out where 41 pi over 11 is. So I'm going to draw our good old quadrants here. And let's think about where this is. Now, since we've got fractions with an 11 on the bottom, pi, 1 whole pi, is going to be 11/11. So let's just kind of keep track where we are. So we start with 0. We're now at 11/11. Come all the way around, we're at 22/11. 33/11, which means we need to go 8/11 more. Well, 8/11 more is going to bring me somewhere over here. So there is my angle, 41 pi over 11. So what I need to do is figure out the angle in this interval that is coterminal. So it has the same tangent value. So what I'm going to be looking for is this guy. So the question is, how far away are we going in this direction? So how I would attempt this is think about how much more would I have to add here to get all the way to 4 pi? Well, 4 pi would be 44/11. So I'm 3/11 away. So this is minus 3 pi over 11. So basically what we know then is that this is the same as the inverse tangent of the tangent of minus 3 pi over 11. I know that these are equivalent because these angles are coterminal, and coterminal angles have the same trig function values. But now minus 3 pi over 11 is in that interval. So the tangent and inverse tangent just cancel. And I'm left with minus 3 pi over 11. So this is how I approach it. There are other ways. But basically, I like to figure out where my angle is. So I draw this picture or I mentally think about it. And then I use that to get myself back into the correct interval. It turned out that this one was exactly where we wanted to be. It was in quadrant 4 or 1. If I had ended up with one, let's say that I had something that was, say, like down here, what I would do is I'd say, all right, I know tangent here is positive because it's quadrant 3. So if I have one that's in quadrant 3, I'm really looking for a first quadrant angle, which is going to be this guy. And so I would use reference angles to get back there. So some of it is well, you got to adjust depending upon what this angle is. and my specific interval. But if you end up in those quadrants, just find the coterminal angle and then you're good. All right, so does that make sense? Does that help?
Yeah, it's help.
Okay, good. All right. So I think we're going to go ahead and move on. If you still have homework questions, please feel free to send me a message or find me during my office hour. Real quick while we're on the record, I have to adjust my office hour a little bit today. I'm actually going to be doing 2 half-hour office hours. First one's going to be from 12:30 to 1, and the other one's going to be from 3 to 3:30. I had another meeting that popped up during my usual time. I will send out a message as soon as we're done with class. I'll put it up on Canvas so everybody can see that, but just so you're aware, things are going to be slightly different. But if you still have questions about homework or anything, again, reach out to me and I'll do my best to help you out. Just realize that this first set, all the pre-calculus stuff, it's due tonight at midnight. Well, technically 11:59, but. All right, so I'm going to hop to the whiteboard and we're going to go ahead and continue our discussion of limits. All right, so last time we started talking about limits, and let me just sort of remind you what's going on with limits and what that actually means. So the idea of limits, again, we have something like this, the limit as x approaches c of f of x. And what we're really looking at here is, in words, is what is happening to the function as we approach x equals c. It's not what's happening at c. I don't care what's happening when we're exactly x equals c. I'm more concerned with what's happening as we're getting close to c. And I showed you last time a couple of ways that we could approximate this, right? And so in terms of the ways of evaluating these things, there really are 3. So the first thing you can do is you can do a graphical, and I'm going to put here guess. Again, to kind of go with my discussion earlier, math students don't like guess. We don't like that word because we want to get the value, right? But when we look at it graphically, we're making a guess. And hopefully you kind of remember what we did when we were trying to do this graphically, is that if you have a graph of a function, so let's say this is our function, and we're approaching c, the way that we want to think about this is, imagine that you're just crawling on here. I like to think of it as a spider, right? Crawling on the function. What happens to that spider? What happens to its elevation as we approach from either side? And in this case, we notice that as the spider moves closer and closer to C, meaning left and right getting closer and closer to this value, that the elevation becomes the same and would be something like right around here. So I'm going to call this L, big L for limit. All right, so this would be what our function value is. But you can graphically guess. So if you can draw the picture, you can kind of follow it along and see what happens. All right, so you can make a graphical guess, but you can also do a numerical guess. And this was the one where we plugged in X values that were very close to C. And let's see, there was some sort of a pattern. And so we were doing this just a second ago when I was talking about making a guess for the instantaneous rate of change for a function, right? But let's just say, let me take the numbers. We saw with those X's, I think I was doing 1.1, 1.01, 1.001. So let's say we have this going on. It definitely looks that the closer we're getting to 1, the closer our function value is getting to 2. So this would lead me to a guess of 2. And like I said, anytime I do this with numerical approximations, I always end up putting a question mark over it because I don't know. I don't know. I have a good guess, but I don't actually know. So both of these are making guesses, which, I mean, that's good. It's better than nothing. At least we have an idea of what's going on, but it's still a guess. And what we want to start working on is how do we eliminate guess? How do we make it so that we've got exact values? And so that's what we're going to do today. I'm going to introduce you to some limit laws, some limit rules. We're going to use those, and then I'll show you some algebraic techniques that we use to help us when we actually want to evaluate limits. Okay, so this was the idea of limits. It's what's happening as we get close to, but we don't actually care what's happening at that location, right? We just want to be close to that value. Another thing that I showed you that I want to remind you about are one-sided limits. So hopefully you remember those from last time as well. And one-sided limits are exactly what they sound like. They're limits, but only when we're coming from one side. And so if we're going to take the limit from the left, we're going to write the limit as x approaches c, and we put a little minus sign as an exponent. And then the limit from the right, that was the limit as x approaches c, but we put a little plus as our exponent to remind us that we're coming from the right-hand side, from the positive side. So you can do one-sided limits instead of total limits. And one-sided limits are actually a little bit better, or nicer, I should say, easier, because we only have to worry about one side instead of worrying about coming from both sides. So graphically, we don't have to worry about being the spider on both sides. We just look at the spider on one side. Numerically, we only look at numbers that are bigger than C, or only numbers that are smaller than C. And so it really cuts down our work if all we're doing is looking at one-sided limits. And I remember the example that I showed you when it came to one-sided limits. We looked at the limit as x goes to 0 of absolute value of x. So I'm going to go ahead and write those two one-sided limits. And we saw that for the first one, it was 1. So the one coming from the right, it was 1. So if you plug in numbers that are bigger than 0, the numbers that come out are 1. When you put in a number that's smaller than 0, the numbers that come out were -1. And we actually saw this on the graph as well. The graph of this thing looked like this. So again, you can imagine if you're the spider walking along on this lower one, you're always at -1. And as you get closer and closer to 0, you still get -1. But from the right, your y value is always +1. So this was a case where the one-sided limits were not the same, unlike other examples that we'd seen so far. All right, so one-sided limits, we do these a lot. just be familiar with what those actually mean. This does not mean positive 0 and negative 0. It means 0 from the right and 0 from the left. All right, well, it turns out that for a limit to exist, so the limit as x approaches c of f of x equals L is only true, or let me put only exists if the one-sided limits are equal to each other and are also equal to that value. So in a situation like this one, with the absolute value of x over x, what we would say is that the limit itself does not exist. And it doesn't exist because we're approaching two different values as we come from the two different sides. So this is something we definitely want to watch out for, because if we're going to try to find limits, sometimes they don't actually exist. And this is one of the ways that they may not exist, is if if the values are not the same coming from each side. While we're at it, let me show you some other places where limits don't exist. So maybe we'll even start making a list here. So when does the limit fail to exist? Because that's probably a good question just to have in our mind anyway, is that are there going to be times when this limit doesn't exist? So the first one is when the one-sided limits are not the same. So let's go ahead and put it here. So the one-sided limits are different. On a graph, that means there's always some sort of a jump. We're approaching two different y values, so there's a vertical jump somewhere. That's what you'd see on a graph. In terms of the data, the numerical stuff, you'll just see you're getting closer and closer to two different numbers. All right, so this is one place that limits fail to exist. Another one where they fail to exist is when we have infinite behavior. All right, basically what I mean by this, let me put it into words you've seen before. This would be a vertical asymptote. So this is a line, vertical line, that the function approaches but never crosses. So let me give you an example of one of these, another super easy one. And that would be our friend, the butterfly function. Actually, no, let's change it to 1 over x squared. So we're going to look at the limit as x goes to 0 of 1 over x squared. So let me show you what happens numerically, and then let me show you what happens graphically so you can see this infinite behavior. So let's start by plugging in numbers very close to 0 and seeing what comes out. So we'll put in 0.1, 0.01, 0.001. And then because we want to make sure that the other side is being taken care of as well, let's put in the negatives of these. Since it's not a one-sided limit, we actually want to look both directions. All right, well, if I take 0.1, put it in here and I square it, I get 100. Okay, so 1 over 0.1 quantity squared is 100. If I go to 0.01, I get 10,000. If I put in 0.001, I get 1 million. So notice that as I'm getting closer and closer to 0, these numbers are getting really big. Similarly, if I put in the negatives, since I'm squaring, it just turns positive. So we see the exact same pattern when we're coming from the other direction. But either way, as we move closer to 0, these numbers blow up. Okay, so infinite behavior. That's what I mean here. They grow without bound. Graphically, what we're seeing here, 1 over x squared looks like this. So again, imagine that you're walking on this graph and you're approaching 0. So let's approach from the left. So I'm walking on that graph and my y value just keeps getting bigger and bigger and bigger and bigger. I'm just going to keep going up and up and up and up and up and up and up forever. So again, infinite behavior or vertical asymptote, right? You can see that vertical asymptote right here. So in this case, what we would say is that this limit does not exist. And it's pretty standard to use DNE to say does not exist. Okay, so if you ever see that, DNE does not exist. So there's another time that the limit will not exist, and that's with infinite behavior. But I will tell you that this is one place where mathematicians will still write what this limit equals. Even though it doesn't exist, what you'll see mathematicians write is infinity. And I apologize on behalf of mathematicians for doing this, because it doesn't really make sense to be like, hey, it doesn't exist, but we're still going to say it is infinity. But infinity is a weird thing. It's not actually a number. It's not. It's more of just the idea of going on forever. And this is the mathematician's way of getting a little more information. If I write equals infinity, that tells me something. That tells me my function is flying upward. You tell me my limit doesn't exist, there are lots of reasons it may not exist. But if you tell me equals infinity, then I know exactly why, which is a little bit better information. Okay, so that's why mathematicians will do this. If it had been going downward, we would have said negative infinity. You put a minus infinity in front of there. So for example, if we were to look at the butterfly function, remember f of x, if we did a one-sided limit on that, so like the limit as x goes to 0 from the right of 1 over x, we would write is infinity. The limit as x approaches 0 from the left of 1 over x, we would write negative infinity. So notice that there's a minus sign there, because what that tells me is that I've got infinite behavior, but down towards negative infinity. So recall the graph of 1 over x, and you can see exactly this. So that's our friend the butterfly. So there's still a vertical asymptote at 0, but as we approach from the left, our spider goes down forever. As we approach from the right, it goes up forever. So for Aaliyah, it's a good question. She just said, would I rather that you guys write do not exist or plus or minus infinity? It depends on the context, but in general, I would rather have you write plus or minus infinity, because again, that gives a little bit more information. But if you wrote does not exist, you'd actually be 100% right. Just like if you were to write equals infinity or minus infinity, also correct. So it's one of those Maybe you have your own personal preference. I personally like writing the infinity or minus infinity because it tells me more. But that's kind of up to you guys. All right, so infinite behavior. It's one of those weird things, but limits definitely don't exist. There isn't a number that we're approaching. There are a few more. There's one more I want to give you, and this is, I'm just going to put here some sort of weird, or let's say some odd oscillating behavior. This is Bruce speak. I don't know if there's actually a term for this, but let me give you an example of what I'm talking about. Let's say we are going to have a function f of x equals sine of 1 over x. And we're going to look at the limit as x goes to 0 of this. So you can just start plugging in numbers. And you might think, okay, hey, I'm dividing by 0. So we have sort of the same issue that we had just before with the butterfly function, that this thing is just going to blow up. But remember that sine is always trapped between plus and minus 1. Right? No matter what you plug in, you always get something between plus or minus 1. So we don't actually have infinite behavior. It doesn't grow forever. But what would happen if you were to draw the graph of this thing, right? Sine oscillates between plus and minus 1. So over here, it's oscillating. But what ends up with that oscillation gets faster because we're plugging in larger and larger numbers. And so pretty soon, what's happening as we go to 0 is it's just flying back and forth between plus and minus 1. And there isn't a specific value that we're getting closer to. As we move closer and closer to x equals 0, this thing keeps bouncing between plus and minus 1. And so that's what I mean by this. It's just weird. Maybe weird's a better word than odd, but it's weird oscillation. We get this oscillation that can happen from time to time. All right, so there's another one. And then I'm just going to put ... because there are more. But basically, if you wanted to just say in words, like if someone says, what are you studying? Oh, we're learning about limits. This is what they are. And then someone says, oh, okay, but then do they always exist? And you go, well, no, they don't. There are times that they fail to exist. And really, you can break it down into something this simple. You can just say that the limit fails to exist when there isn't a single value that the function approaches. So there has to be just a number, one value that your function's actually going towards, right? So there's got to be the one number, and if it's not there, then this limit doesn't exist. All right, so basically we need to keep our eyes open for that. Look for problem spots, and if the problem spots are there, some sort of weird thing where we're not approaching a single value, we say our limit doesn't exist. In the case of the infinite behavior, yeah, we can write equals infinity or minus infinity, but that's just for more clarification. But in reality, no, the limit does not exist. DNE. All right, so yay. Maybe we're starting to feel a little bit better about what a limit is. Again, it's what's going on as we get close to the value, not what's happening at the value, right? I don't care what's happening, like with that sine one. I don't care about x equals 0. I don't care about that at all. I just care about close to 0. All right, well, let me give you some rules that are going to help us when it comes time to evaluating limits. Okay, and then we're going to use these rules to help us evaluate these things faster so we don't have to guess. Even if it's a good guess, we don't want to guess. We want to be able to have the value. All right, so I'm going to call these limit laws. Laws are a little bit better than a rule, or it sounds better than a rule, right? No, this is the law. This is how it is. Okay, so first things first. Let me just give you this one. We're going to take a limit as x goes to c of a. Now, a, this is a constant function. Okay, this is say like we're taking the limit of 3 or the limit of minus 11 or whatever. Pick your favorite constant number. So let's think about this from the graphical approach. And so the function f of x equals a looks like this. Whatever a happens to be, right? It might be down or up or higher or whatever, but it's a horizontal line. It's a constant function. So let's pick our favorite c value because it doesn't really matter. Let's just say that this is c. So think about this graphically. Imagine you're a spider walking along. What's happening to your y value as you get closer to it?
Stays the same.
Yeah, it stays the same. It's always a, right? You're staying horizontally, and the same thing happens if you come from the left. Well, think about doing this numerically. Plug in numbers. Okay, so if I'm a little bit bigger than c, I'm going to get out a. As I move in, I get a, right? It stays the same. And so because all those values are always the same, because it's a constant function, this limit is a. So basically what we're saying here is that if you have a constant, the limit, no matter where we're approaching, is always that constant. That probably feels silly, bordering on dumb. Well, yeah, duh. But it's good just to have this written out explicitly. This is how it works. Okay, so there's your first one. Here's your second one. Let's take a limit as x approaches c of x. So we'll take the most basic function that's not constant and do the same thing. All right, so what does this look like? What do you think? What's your guess of what this limit is? No guesses? All right, well then let's do it numerically. Let's figure it out. Let's pick a specific c value and evaluate this limit. So let's just say we're going to let c equal 2. So let's go with numbers that are getting closer and closer to 2. All right, well, f of x is just x. So that means whatever you plug in is what you get out. Let's come from the smaller side as well. So what is it looking like as we approach c from both sides? As we approach 2 from both sides, what are we getting? What's it looking like the function looks like? Okay, so Bailey just said itself. Cool, this one definitely looks like it's approaching 2. And so that is true. It turns out that we're approaching 2, well, the function is approaching 2. So in this case, if we're approaching c, then the limit is going to be c. And this one should also just make total sense if you think about how this function works. This function, we actually call it the identity function, because whatever you plug in is what comes out. So if we're going to plug in numbers that are near C, we're going to get values that are near C. Duh. All right, so this one, the limit as x approaches C of x is just C. All right, now I'm not going to do any other basic functions. So I'm going to give you some sort of bigger overarching limit laws. But these two, in addition to these other limit laws I'm going to give you, are what going to make it so that we can just do this algebraically. So here's your next one. If you have a limit, you're evaluating a limit of a sum of functions. And I'm actually going to put or different, so plus or minus. This is the same as evaluating the limits of their functions separately and then adding or subtracting. And I don't know if you guys hear that like humming in the background. I apologize. There's construction going on across the street, and they're doing something that's kind of loud on my end, so you probably hear it as well, but I apologize for that. But let's come back to this one. So if you add or subtract functions, you can actually split them apart and do their limits individually. Now, I'm not going to prove this, at least not right now, because I need to give you a little bit more information technically what a limit means if we're going to try to prove some stuff. But for right now, I just need you to smile and nod and go, yep, okay, that sounds good. So this is what happens when we add and subtract.
Would you be able to?
So it's hard to see that one with the glare. Thanks for letting me know. I'll rewrite that over here then. So we got the limit as x goes to C of f of x plus or minus g of x. Okay, so that's the same one. You're welcome. Thanks for letting me know. So adding or subtracting, just you can do them separately. What's even better is that there are similar rules for multiplication and for division. So if you have two functions that are being multiplied, whose limit you're taking, you can actually split that one up as the two separate limits and multiply them. And similarly with division. So I'm going to put another one over here for division. So this is actually kind of nice, because this just means that all those operations you learned back in the day, add, subtract, multiply, and divide, they still all work with limits. And so you can have this huge, horrible expression that will actually be able to simplify down into expressions using rules. All right, so let me show you how we use these rules to evaluate a more complicated function. So for example, let's do limit as approach 1 of x over x squared plus 1. So on what this limit is. So I'm going to start by using the limit laws, and specifically the one I just wrote, the one with the division. So this is going to be the same as the limit as x goes to 1 of x divided by the limit as to 1 of x squared plus 1. So I just use the fact that since I had division inside my limit, I can write it as two separate. Now, the one on top, I'm just going to leave it for right now because we can evaluate it. This is the, what is it? I think the second of the laws that I gave you, right? The limit as x approaches c of x. We know what to do with that. So let's keep going with this one on the bottom. So on the bottom, I've got addition. So let me split that into some addition problems, addition limits. So I've got the limit on the bottom. I've got the limit as x approaches 1 of x squared plus the limit as x approaches 1 of 1. So again, let's just sort of track which ones we can evaluate. We know we can take care of the top. Now on the bottom, I know we can take care of this last guy. This is the first rule I showed you. If your limit is, the function is a constant, we just get that constant. So that one's good. Which leaves us with the limit of x squared. Now, I didn't give you a rule for powers, right? There wasn't anything there that had powers, but I did give you a rule for multiplication. And remember that powers are just repeated multiplication. So what that means is that I can actually think of this as x times x, which means I can split that into 2 using the multiplication rule. So we're now going to have the limit as x goes to 1 of x divided by the limit as x goes to 1 of x times the limit as x goes to 1 of x plus the limit as x goes to 1 of 1. And now we're ready to evaluate all these limits. So the limit as x goes to 1 of x is equal to 1. We already saw that whatever goes in is what comes out. So if we approach 1 in the x's, our y's are going to approach 1. On the bottom, these two limits are both 1 for the same reason. And then this last guy, since it's a constant, we just get that constant value. All right, well, your arithmetic on that, and you get 1/2. So we know this limit is 1/2. This isn't a guess anymore. This is the limit. So I don't put a question mark over it or anything. I know that this function approaches 1/2 as we get close to 1. And if you were to plug in numbers close to 1, like try it. Put in 1.01. Put that into your calculator, see what number you get out. You're going to get something very close to half. You're not going to get 1/2, but you'll get something pretty close to it. And the closer you get to 1, the numbers you put in that are closer and closer to 1 are going to get you a number that gets closer and closer to 1/2. If you draw the graph and you think about walking on the curve like a spider, you're going to see that you get closer to 1/2 as you move in. But this is far superior because this is not a guess anymore. This is the answer, which should make all of you happier. I know it doesn't, because this sucked, right? This sucked, having to kind of break it apart. And this was a pretty basic, not too complicated function. You can imagine if it gets to be big and nasty and gnarly, this is a little rough. So I get that, right? This sucks. But on the flip side, it's no longer a guess. It is the answer. All right. So are you ready for the good news, though? Because there usually is, right? It turns out that we can do this much faster. We can do this way faster. We don't actually have to split it into all the different rules and go through that. I did that here so you can see how those rules are being applied. But now let me show you how we actually do this. Okay, this is how it's actually done when you're given a limit. So here's what you're going to do to evaluate a limit. Okay, step one. You're actually going to plug in x equals c. You're going to plug in that value that we're approaching. Okay. If this is defined, it is your limit. So let's go back to this guy. We had the limit as x approaches 1 of x over x squared plus 1. I'm going to make that a little darker. Okay, so step number one, plug in x equals c. Well, that's 1. So we're going to do 1 over 1 squared plus 1. Hey, that equals 1/2. It's defined. That's our limit. Okay, well, I can't tell if you're actually happy about this because I don't hear you guys cheering. I don't see any, big zaws. There you go. Thanks, Bailey. But this should make you really, really happy because it turns out that even though, remember, the limit we're talking about, I don't care about what happens at 1. I care about what happens near 1. Well, most of the time, those are the same thing. So can I say that one more time? Oof. Which part? That, no, yeah, seriously, errors. I don't know about that. Oh, just the last part. Okay. So even though limits talk about being close to that value, what's happening near that value, not exactly at that value, it turns out that for lots of functions, those are one and the same. What happens as we get close to a number is the same as what happens at that number. And so for all of those functions, that's all you got to do. You just plug it in and you've got your limit value. But super important is this word, as long as it's defined, because if it's not defined, then we're going to have a bit of an issue. So let me show you a situation like that where we run into a problem just plugging it in. And this is actually one, I don't know if it's exactly the one that we did before, but it's similar to one that we did before. All right, oh, I should probably add here. So if this is defined, then it's your limit. And then I'm going to put 3. If it's undefined, we're going to have to try something else. What that something else is, there's actually a huge list of things that you can do for that something else. I'll start showing you some of them. We'll pick up more of them as you go along in this class. Like later this quarter, I'll give you another one. It's called L'Hopital's rule, which is super awesome, but we need to know the derivative to do it. And of course, we're not there yet. Okay, so in general, we try plugging it in. If that doesn't work, then you got to try something else. So let me show you an example of one where plugging it in doesn't work. So let's look at the limit as x approaches 1 of x squared minus 1 over x minus 1. I think this is one we did the other day. If not, it looks a lot similar to this. Okay, so let's plug in those numbers and let's see what happens. So if we just try plugging it in, we're going to get 1 squared minus 1 over 1 minus 1, which is 0 over 0. So now this is probably bringing back a little bit of, your memories are coming back probably a bit, because we talked a little bit about how 0 over 0 is a weird thing and it can actually equal any number whatsoever. And so we run into 0 over 0, which is not defined. I'm just going to put here undefined. So we immediately drop then into that number 3. All right, well, it's not 9, so we got to try something else. So this is going to happen to you. It's gonna, where you try to plug something in and you end up getting 0 over 0 or something else that's undefined. And then we have to try something else, figure out what the limit is. So we can get to a graph. We can plug in some numbers to get approximate. But again, I want to get exact answers. And so I need to show some algebra to do this. Okay, so some of that, try other things. So let me just put other things to try. And let me see if I can limit that glare too real quick. That's a little bit better. Okay, so other things that you can try. I'm going to give you some algebra things. So the first thing under algebra that you can use that sometimes helps is factoring. Because sometimes you can factor and the factor can simplify. Another thing that you can try is rationalizing. Rationalizing, that means eliminate the square roots. Both of these have very specific forms where it can help. Remember, with factoring, this one we need polynomials. And for rationalizing, you need roots. So these two specifically, there are forms that will push you in that direction. Like if you look at this first one, the one that we just tried right here, factoring is what we're going to try because we've got polynomials on top and bottom. So it seems pretty natural to try factoring. We wouldn't try rationalizing because there are no roots. You're only going to try rationalizing if there actually are radicals. Okay, so these are the two big algebra things that you can try. There's also trig stuff that you can try, specifically identities, because the trig identities combined with algebra can simplify it and sometimes get it into a form where you're going to be able to make it work. So I'll show you an example of each one of these, at least one example of each one of them, just so you can see how they play out. All right, now other things to try. Again, I'm going to put ... because there will be more. There are other things that we can try, but those will come as we go. All right, so let me show you this first one, how factoring can help with this limit right here. So when we plugged it in, we got 0 over 0, told us, well, we got to try something else. But let's try factoring. So notice x squared minus 1 is a difference of squares. So I'll go ahead and do that. So x squared minus 1, that's equal to x minus 1 times x plus 1. Okay, so you can probably start seeing then why this is going to be useful. Because what are we going to do now?
Cancel out.
Yep, we've got those x minus 1s. We can actually cancel them off. Right? We can cross those off because we know that when you take something and you divide by itself, it just turns into 1. So in essence, it goes away. Now, this is super dangerous when you have variables. It's super dangerous to just start slashing stuff because it doesn't always work. You may have run into this problem when you've solved equations and things in the past where you lose information when you do this. But let me assure you that that's okay here. Because think about this, x minus 1, the only time that we might have an issue here is if x is equal to 1. If x is equal to 1, then I'm dividing by 0, and I'm basically trying to cancel out zeros, which is always a problem. But here's the good news. Remember what we're doing is we're taking a limit. And the limit is saying what's happening as x gets close to 1. I'm never actually at 1. I'm really, really close to it, but I'm never actually there. So x minus 1 is never actually 0. It's really close to 0, but it's never actually 0. So I can legit cancel those out. And these limits are the same. The limit of the original is the same as the limit as x goes to 1 of x plus 1. If you were to look at the graphs of these two functions, x squared minus 1 over x minus 1 and x plus 1, the graphs of those two things are identical. You wouldn't even notice a difference because the only difference is that this top one has a hole. It has one little tiny hole that happens to be when x is at 1. So other than at that spot, these guys are identical. Well, now I've got a function that I can just plug in. I can plug in 1. And when I plug that in, I get 1 plus 1, which is 2. And I'm pretty confident that this was the function that we looked at last time. And if you go back and you look at what numerical approximations we were finding numbers that got really, really close to 2. But now we know that this limit is 2. So factoring, top and bottom, that's one of the big techniques. So you might need to practice your factoring. You might need to review that a little bit if you're a little rusty. But it's terribly useful when you run into something like this. Let me show you a rationalizing one, and then I think we're going to call it a day. So here's an example of one where rationalizing would help. And that would be something like, let's say the limit as x approaches 4 of the square root of x minus 2 over x minus 4. So start the same way that we did before, which is the what happens when we actually plug in 4. So if we just tried plugging in 4, we'd get the square root of 4 minus 2 over 4 minus 4. I don't think I really need to go much further than just look at the bottom, right? We have 4 minus 4 is 0. And so because of that 0 on the bottom, I know that this is undefined. And so we're going to have to try something else. It turns out the top is also 0. So we get that same indeterminate form of 0 over 0. All right, so here's what we're going to do. We're going to try to rationalize.
If the top value is
what's that?
If the top value isn't 0, is it just undefined?
It's still undefined. At that case, then it would actually either be going to plus or minus infinity.
Okay.
And we'd want to try to figure that out.
Okay, cool.
But yeah, if it had been like 4/0, we know for sure the limit is undefined or does not exist. All right, now I know that when you learned rationalizing forever ago, you were always taught to rationalize the denominator, the bottom of the fraction. In this case, we're going to want to rationalize the numerator. We want to rationalize the top. So the way to do that is you use the conjugate. So I don't know if you remember this exactly, but what we're going to do is we're going to multiply the top and bottom by the same thing, but we're going to multiply by root x plus 2. So we're going to multiply by the square root of x plus 2. I got really dark here. Hold on. See if that helps a little bit. Yep, that's a little bit better. Okay, so on the bottom, I'm going to leave it just how it is. So we've got on the bottom here, x minus 4 times the square root of x plus 2. And on the top, I'm going to multiply that out. So I'm going to FOIL. Root x times root x is x. I get plus 2 root x minus 2 root x, so those go away. And then minus 2 times 2 is minus 4. And that's the whole point of rationalizing, is that it makes it so that the radicals go away. I'm left with just x minus 4. But you can probably see now what our next step's going to be. I've got an x minus 4 on top and x minus 4 on the bottom, and I can cancel those off. So that leaves me a limit as x goes to 4 of 1 over the square root of x plus 2. So again, these two are exactly the same, except for x equals 4. This one had a hole in it. But now we're looking at the function that doesn't have a hole in it, and we can actually plug these numbers in. So we're going to get 1 over the square root of 4 plus 2, which ends up being 1/4. And so if you numerically put in numbers near 4, go back to the original function and put in 3.9, 3.99, 3.999, and so on, you're going to get values out that are getting closer and closer to 1/4. But this isn't an approximation anymore. This is the answer. This is the limit. So we're going to play algebra tricks like this all the time in order to help us figure out limits. All right, I'm going to go head back to my computer here just for wrapping up today. All right, so we're going to do more of this. We'll definitely talk a little bit more about how to do limits, how to calculate them with algebra. I'll show you some trig stuff. So we're in the middle of, I think, section 2.3. We're almost back caught up, but we're somewhere in there, I think. I also kind of bounce around a little bit in the sections just for whatever seems appropriate at the time. So we may have we might have dove ourselves into 2.4 or something else like that. But we're going to keep talking limits. I want you to get a little bit more comfortable with them. But it really is going to be a lot of algebra for us to actually calculate the values. But it'll come. It'll be easier for you as we go along. All right. So with that, I'm going to go ahead and pause our recording here.